Hello and welcome back to module number 5. We are going to cover in this chapter number 8. So let's begin. Today's topic, we're going to talk about probability and the idea of what does it entail, and we're going to talk about that in the realm of distribution and how it apply. I want to back up a little bit to module number 4, where we talked about probability concept. We talked about sample space. We talked about events. We talked about simple probability and joint probability. We talked about condition probability, and we started to talk about random variables and probability distribution. So in this case, in this module, I will also cover another aspect, discrete probability distribution. I'm going to talk more specifically binary and binomial distribution and Poisson distribution. And we are going also to talk about continuous probability distribution, uninformed and normal. So I will try to reach out with that regard with regard to probability distribution. So I will fix the screen so it will be clear. Okay, so there are probability 3 ways. We talked about that last time, about process of generating events is known, and this is the idea of computing using classical probability definition. Example, rolling the dice. The second is relative frequency. We are usually using computing power to examine empirical data. Rain day next day based on history, and again the frequency is part of the history, and as a result I can make assumption that every first week of October in Tampa it is raining. So this is again taking past history in order for me to be able to predict what will happen next month. The next subject, the third subject, is subjective method, and this is based on a judgment. Example, we are going to see a lot of politicians saying, "Oh, I'm going to win the election." This is a subjective methods, and how the politician make this ruling is something that we need to judge and to be critic of. So what are we going to talk about? We are talking about the first element is random variable, and a random variable is a subject due to changes or the result of. So the variable can take a set of different possible values. In the book, I provided the example of rent, but most famous example is flipping a coin. In R, when we are flipping a coin, we usually, or generating a random number, we have a command for samples, selected size, and the number of random number you want to retrieve the sample size that you select. So example, the command is sample, 1 to 40 is the number that I want you to select, and I want 4 random numbers. So this is how it's been done. So another function that is really important is the runIf function that allowed us to generate numbers that are where any value, including factorial values, can be added. So example, if I will say x1 and I will say runIf, and I will say I want you to add to the equation or to the sample the numbers 1, 5.1 and 7.4, and the result will give us the idea of adding those numbers into the equation or the outside. Back to where we start in module number 1, types of data. We talked about categorical data, we talked about numerical data. Just a reminder, categorical data Are you married or not? What is your political party identification? What is the color of your eyes? Numerical, we have two types, discrete versus continuous. Discrete is the number of children. Continuous is the weight. And today I feel fat, but if I will run this afternoon and not eat a lot of ice cream in late evening, maybe I will lose weight. And so the weight is something that can change at times. Compared to the number of children, is usually steady. So this is the idea of discrete versus continuous. So in discrete random variable, the discrete obtained by counting 1, 2, 3, etc. Usually the infinite by the number of different values. So if we toss a coin 5 times, count the number of tails, we will have the same thing: 0, 1, 2, 3, or 5. In discrete probability example, this is a pure example of tossing 2 coins. So you have what is their value and what is the probability distribution out of it. When we are talking about probability distribution, the possible value that a random variables may assume along with the probability of assuming those values. And this is important for us to remember about probability distribution. Discrete probability distribution is the list of all possible values, which include the x and the p multiplied by x. So the p is the value of the random variable. The p multiplied by x is the probability associated with the value. Just a reminder, mutually exclusive is nothing in common. Collectively exclusive is nothing left out. So this is the formula that we often apply to when we are talking about mutually exclusive versus collectively exhaustive probability or distribution. In R, with regard to discrete probability distribution, I have 2 sets. I have x and y, and if I will plot it, I will be able to show this is what it will come. So I have 2 lists. Basically, they are the same, but what I want to show you that we can improve the visual by example adding the plot x and y with a pitch of 16 and the color dark red in order for us to see it better. Next, the sample space. It is collection of all possible outcome. For example, all 6 faces of a die or all 55 cards on a bridge deck. So this is something that we are talking about sample space. This is where we lay out what is the foundation of our count. So simple event is the outcome from a simple space with 1 characteristics. Example, red card from a deck of cards, or in a case of joint event, involve 2 outcome. That is the ace, which is also a red card from the deck of card. So joint event is an ace and a red card. If I will visualize it, and which is really important, again, we have a form of table that allowed us to do what it is, and in this case, the black and the red, and how it display in distribution or in contingency tables. One of the ways in the past, and I'm sure that it will be helpful in the future too, is to show the tree diagram. It layouts where is all the possible outcome of the probability. So if I have a full deck of cards and we have red cards and we have black cards, we have ace and not ace, and I can maneuver where my cards are with that diagram. So this is the idea of that. Another way for us to do is with the simple events. There are 5 happy faces in this collection of out of 18 objects. So it will allow us to see where those faces are and how they apply. Another element that we have to remember with regard to the terminology in probability is the independent versus the dependent events. 2 events are independent if the occurrence of one does not change the probability of the other. Example, if we would roll a 2 on a die and flip a head on a coin, if events are independent, then the probability of them both occurring at the same time is the product of probability of each occurrence. So, what is the definition of independent event? And what is the definition of the dependent event? I will start with the dependent event. When 2 events are said to be independent, the probability of one of the event occur will influence the likelihood of the other event. In comparison, the independent is that one will affect the other and there is no influence what the other one being outline of the other one. So I hope that makes sense. I hope it will occur. So again, 3 items: happy face giving light colored, and this is the outcome. So again, happy face and the outcome of it. How do we compute probability? So the probability of event E is the idea of the following formula. The probability E is equal to the number of outcomes divided by the total number of possible outcomes in a simple space. And this is important. It's basically the idea of X divided by T. Each of the outcome in a sample space likely to occur. And this is important. How do we outline the computing the joint probability? Again, the P is the key component and it holds A and B. So the number of event outcome from both A and B divided by the total number of possible outcome in a sample space. So the contingency table will represent the following: event A and event B, event A1 and event A2, event B1 and event B2, and the total in order for us to lay out the foundation. The probability of compound event A or B, so the number of event outcomes from either A or B divided by the total outcomes in a sample space. Additional rule, and again, this is for mutually exclusive events. A or B equal the probability of A plus B, and this is how we calculate that. We have A1, A2 and the total, and we have B1, B2 and the total in order for us to calculate that, in order for us to evaluate that. I gave you the assignment and I hope that the assignment gave you a better foundation of what it means. The probability of event A given the event B has occurred, and this is the outcome of that probability. Again, conditional probability through the eyes of contingency table. Again, conditional event, draw 1 card, and this is what it comes down to: ace, non-ace, red, black, and the total in order for us to calculate that. I think this is a really important because it helps us to see why is it so important, those rules with regard to probability. Conditional probability and manipulation rule, and again, conditional probability A and B divided by B. Manipulation rule is that A divided by B multiplied by B is equal A divided by B multiplied by A, probability of A, and those are the rules that we often defined. Back to our independent and the dependent. So events are independent is when A divided by B is equal probability A, or B divided by A is equal B, and those event A and B are independent when the probability of one event A is not affected by another event B. Discrete random variable measure, then we have standard equation like we did in descriptive statistics. We have expected value, which is the mean, and we have also the idea of averages. So expected value is the weighted average of the probability distribution, and we are calculating it according to mu equal probability of x equal xi multiplied by p multiplied by xi. So it is the idea what it stands for and why we calculate that. But we also, in that idea, we also use standard deviation. So we calculate the standard deviation, and where the variance of this discrete probability distribution allowed us to formulate the following formula, and that's the formula that we apply to. For example, I gave it in my textbook, the probability of library loan program. To generate distribution, we calculate the following value. The probability of px, the probability of x multiplied by p multiplied by x squared, and x squared multiplied by x, in order for us to calculate the idea behind it and what it stands for. So how do we analyze? We compare the mean of discrete random variable, square each value of x and record it in the fourth column of the table, and then we compute the value of x squared multiplied by x, where we substitute the value of the mean using the following formula. So this is how I analyze our idea. Next is the importance of discrete probability distribution. We are talking about binomial and Poisson probability, which is a really important aspect. But in that arena, we have the idea of Bernoulli distribution. It is when two possible mutually exclusive outcomes with constant probability of occurrence. We have success versus and or failure. For example, respond to a telemarketing. The probability of mass function is the probability p if x is equal 1. The probability of 1 minus p is if x is 0. So where the probability of success is how we measure that. Binomial distribution is we have a little bit different settings. We have n as identical trials. Example, 15 toes of a coin or 10 light bulbs taken from the hardware. And we also have two mutually exclusive. In this example, two mutually exclusive outcomes of each trial. So those are the things that we are looking at in binomial distribution. We also have the constant probability of each trial. For example, the probability of getting a trial is the same each time we toss a coin, and each light bulb has the same probability of being defected, the same probability. The sample method is idea of with replacement or with auto replacement, and this is something that we will talk more about that as we go along. Trials are independent, so the outcome of one trial does not affect the outcome of another trial. So binomial distribution function, in this case, it's a little bit more complex, but we have the idea is that it consists of P probability, the probability that X success giving knowledge of N and P. We have the value of X, which is the success in the sample. We have the p-value, the probability of success, and N is the number of the sample size. So in this case, this is how we apply to it in order for us to do that. We can also see how we calculate the mean and the standard deviation in this simple example, and I hope that example will illustrate to you how to do that. I'm sure that most of you are already asking, okay, how do we calculate that in R? Okay, so for every distribution that R handles has 4 functions. It is a root name. For example, the root name of normal distribution is called norm. So the root is prefixed by one of the letters. P is for probability or distribution function. Q is quartile. D is for density, the density function. R is for random. So for normal distribution, those functions called P norm or Q norm or D norm, and for binomial distribution, PB I norm and QB or DB I norm, and so forth. And those are the terminology that we are using. For continuous distribution, the most useful function for doing those to solve this function is the P and Q function. So this is how we will outline it. For discrete distribution like binomial, we will use the D function calculation for the density, which is Fx equal Px equal small x. Binomial distribution, again in R, we will set it up as db I norm, and we will set up the numbers of the space, the 27, size, and the probability of 0.25. And those will be able us to calculate what is the probability of each variable in the distribution. The next one is Poisson distribution. It is the idea that discrete events are interval, which means that the probability of one success is interval is stable. The probability of more than one success is in this interval is 0. So the probability of success is independent from interval to from one interval to another. For example, customer arriving in 15 minutes or defect case on light bulbs. So those are examples of that. So in this case, the formula for Poisson distribution function is as follows. We have the idea of the mean, expected number of success. The E is the based on natural logs, and X is the number of success per unit. So one of the classical question in that type of distribution is find the probability of 4 customers arriving in 3 minutes when the mean is 3.6. So what do we have here? We have all the values that we need to calculate in order for us to do that, in order for us to calculate that, and this is the result of it, which is equal 0.19112. So in that distribution, in Poisson distribution, the mean and the standard deviation, and how do we that's how we calculate. Another type of distribution is continuous probability distribution. We have uninformed, we have triangular, we have norm, and we have exponential. Each one of them has the idea what it can be in the distribution itself. Normal distribution, we learn about that in descriptive statistics, where we're looking for the normal distribution is the normal curve on this on the distribution. The properties of normal distribution, usually the mean, median, and mode are equal to each other. So the idea here is that it is represented as a bell shape or systematic about the mean. So under the area of the curve, it's equal to 1. So this is normal distribution, and we also have the idea of inflation points. It is where we find the external points of the distribution, and we have an idea how to calculate. We also measure the mean and the standard deviation and how to calculate. I gave you example in the slide of understanding the mean and standard, which a curve has a greater mean, and we learn about how to calculate that. And the standard normal distribution, how we did that, and you have that in my slide. I'm jumping ahead, and I want one of the things that usually we do with that idea is that we are using the z-score in order for us to do that. So the idea here is the properties of a standard normal distribution we often apply to z-score, which is 0.500. So it is the idea that the z-score give us indication on the distribution itself. In all times, we used to calculate the z-score and based on it to calculate what is the normal distribution and how to apply to it. And we have a standard normal table how to apply to that. Later on, I will teach you how to apply to it to the standard normal table using a package, and we will get into it later on, but this is the way for us manually to calculate normal distribution. The characteristic of normal distribution, as I said, the issue of the shape depends on the population of the mean and the standard deviation, and we already know about that and how to evaluate that and what is the z-score stand for and how to find it. So finding under the standard normal curve and how to apply to it with regard to the z-score and what does it means to us with regard to the idea of probability. So I talked a lot about discrete probability, and we talked about what is a discrete random variable, what is expected random variable, but we are not done yet, because now I want to move to a little bit closer subject, which is the Poisson distribution, and I will try to teach you that through the eyes of R. So in R, we have functions, as you already know, and R poise is a function used to simulate an independent Poisson random variable. For example, we can generate 15 random numbers with the premises of g equal 4. So the idea is that it will give us the 15 numbers in the ROM of the 4 in that space with regard to Poisson distribution. In the next example, we will assign 100 independent numbers. Again, we will make it a little shorter with a 0.7 as a vector, which is called V. And in this case, it will display the following distribution. So the bar in this case, or the bar plot that I generate, is the distribution of V, capital V equals small v. It is more appropriate than histogram because the data is discrete, not continuous. The theoretical distribution in this case is a little bit more complex, and in this case the V can be equal to 0, 1, 2 or others, and it can be written as a function called d POIS, which is a function that allowed us to do that. So again, a same example, but in this case, a different function. And in this function, the V is equal 3 and the G is equal 2. So in this case, it equals to 0.18, and it will give us the idea what it is consist of. And I can make it a little bigger or smaller, and this is where I calculate the standard deviation using the V as my framework. What I did here is I declared it as a framework, and so the V stands for what it stands and what it allowed us to do, and in order for us to calculate. So the mean, the sample mean is an estimate of the population mean or expected value, and the variance of random variable is calculated by following the following formula. In other words, the mean and the variance are equal in Poisson random variable, which is the standard deviation of gamma, and the Poisson random variable of gamma is equal 2.25 that can be calculated by the hands of the use of lambda in R in order for us to do that, in order for us to do standard deviation, and so forth. So I gave you an examples of an exercise, and I will try to see if assignment to see if it makes sense. I know it's hard. I know it's going to be frustrated a little bit. Use the textbook. Use all the materials that I will post on Canvas in order for you to overcome that, because this is the foundation of statistics and analytics, and I hope you enjoy that. Until next time, have fun.